All right, so now we will look in more depth at the actual applications, which are so critical to give the operator the situational awareness and the tools needed to operate the power systems. And this is whether they are a reliability coordinator, a balancing operator, or transmission operator. Basically, everything is to support the operator at their desk. They typically work 12-hour shifts, so there's someone on 24/7. And here's a very typical setup for a fairly high-end control room. Multiple operating consoles. At an individual console at the back of the room, typically you'll have the system supervisor who has 4 different monitors. They actually may window into different computer systems. One will be for monitoring the actual grid with all the real-time values of what's happening in the network. And then another one might be available for actually logging on and buying and selling power. And then there might be another one for actual being on the corporate email network. The ones that are actually monitoring and controlling the grid will be on their own separate secure network, and obviously having everything being highly secure and encrypted is really important. On the front, you will have typically transmission operators that are responsible for different areas of the system, and a separate desk for the actual balancing operator. And they will have a number of projection systems or backlit LED systems that are showing the overall transmission diagrams and state. So the actual data is coming in from the remote terminal units that I mentioned we covered in the previous session. Those are monitoring the actual power grid, and they are sending their data into the supervisory control and data acquisition system. There may be data links to neighboring utilities, because not only do they need to see the awareness of their own system, it can be very important to see what's happening on their neighboring systems. And then, of course, the top-level reliability coordinator, they will typically have data links to all the underlying transmission operators. The top-level reliability coordinator is just a monitoring function, an advisory. They will not be actually doing any of the supervisory control. So again, this is the supervisory control of opening and closing breakers, controlling transformer taps, and the data acquisition part. Then those applications provide the right data to support the generation apps, which is the automatic generation control, the transmission applications, which model the power system, and then we can have the dynamic applications, which are looking at whether the system can be stable. That's the next generation of application. And then we can have a simulation mode. And in the simulation mode, we actually cut the tie to the real power system, and then the simulation engine stimulates all of these applications as if they are running in real time. So if we're running in simulation mode, we would actually be running in a separate control center from the real one. And that's what we call a replica simulator, where you literally replicate all of the consoles, even the projectors, the computers, and you stimulate that from a mathematical model. In the power system simulator which you'll be using, we call that a generic simulator, because the power system is generic and we are emulating these applications. You will have an emulated version of supervisory control and data acquisition. You'll have an emulated automatic generation control. And so because we emulate that, we don't have to replicate the hardware. We can run it on the cloud, and you have access just through an internet browser. But the look and feel of what you'll be doing with the power system simulator is very similar to what these operators do on a real power system. They are looking at station diagrams with circuit breakers and transformers and measurements. That's the exact. You will have a very good mock-up of that when you're on the power system simulator. In the last, especially since the Department of Energy project started with the RF projects, we've allocated about, the government allocated about $4 billion of what they called smart grid investment funding, and a significant part of that went into what is called phasor measurement units. Phasor measurements are ways of detecting the actual angle of the power system. The fundamental rule in a power system is that you need an angle difference between two buses to make the power flow from one part of the network to another. And we'll get into more detail, but in the past we haven't been able to measure the phase angle. The angle is basically determined upon at what time does the waveform cross zero at the bus. So if the waveform at this bus is crossing the zero voltage level earlier than the waveform at this bus, the power will flow in this direction. We say power flows downhill on the angle. And so it's just recently that we've had very accurate satellite clocks that can synchronize the power from one substation to another, down to microseconds. So that high-speed accuracy of knowing exactly the time at that substation allows us to calculate the number of microseconds between the crossing zero here and the crossing zero here. And so for the first time, we have been able to monitor that value and display it to the operator. And we actually display it at a rate of 30 times a second. So these advanced applications then are required to keep the power system stable and to monitor the oscillations. You're all probably familiar with Galloping Gertie, the Tacoma Narrows Bridge. Remember how that first bridge was built with girders that which were not deep enough, and it had a natural frequency of oscillation. When the wind came through, that bridge actually went into a huge dynamically unstable operation. The whole thing collapsed. The same thing can happen to the power system. The power system can break up into a spontaneous oscillation. You get huge surges of flow from the north to the south of the western system across certain boundaries. And so it's very important that we be able to monitor the oscillations and stability. So when we take a line out of service, for example, there will be oscillations. We want those oscillations to damp out really quickly. So we now can measure those phase angles when there is an actual small disturbance on the system, and if they're not damping out nicely and they're staying sustained, they actually present that to the operator. The operator knows that he has to take some control action. And basically what happens is the oscillations occur across an interface where you're moving power, and the way you damp it out is as you move more and more power across an interface, it becomes more and more unstable. So in those cases, the operator has to know to cut back the power transfer to make the system more stable. So these applications are just coming online right now, and we'll get into more detail. They are much more sophisticated. They are opening up a whole different need for training. In the past, we simply gave the operator these limits, and we said, keep the power flow within these limits and everything will be safe, Joe. Now we're running these, but those limits are very conservative because they're based on offline studies. Now, or some cases, those limits, the power system may get into a state where the offline several events may happen which they haven't been able to pre-study. So it's much more important to have the applications running right there to determine what are the safe limits for moving power across the system. So that's basically what these applications are doing. A system can collapse basically due to several phenomena. Transmission lines can be overloaded. What happens when they get overloaded? If the current is too high, the conductors heat up. As they heat up, they expand. As they expand, they sag. So if you're driving along the freeway and you see, boy, that transmission line looks really close, if the operator doesn't watch the flow on that line could sag all the way down to where it could be, flashing over with a high semi-trailer truck, or it could sag into trees. So we call the thermal limits. And that was the major issue where the trees grew up too high and the lines sagged. That was the major cause for the 2003 Northeast blackout. So in summary, I think I might have mentioned, but there are three causes of blackouts. We call them the three T's. Trees, tools. This is having the right tools. If the tools are not working, the operator doesn't have the right visibility, and the training. If the operator is not trained correctly, blackouts can occur as well. So these are an advanced set of tools to really help the operator's situation awareness, and we'll get into more detail of those as we go through the other courses. And this shows what's called, more and more people are talking about control center analytics, how to run various applications to improve their situational awareness. And we will get into all the details of the models required and what are the inputs and outputs for these applications. So this is looking at some of the more advanced analytics that are primarily being installed at the reliability coordinator level. Those are the main organizations that have the responsibility for making sure the grid is managed correctly. Now, at the current point in time, there are a number of challenges. We have what I call the power engineer and the power system operator gap. Engineers in general are trained to run computer programs and study systems in great detail and make decisions in time frames of days or weeks. Power system operators have to respond to real-time conditions and make decisions within time frames of minutes. Power system operators have often come up through the ranks from being substation operators, linemen, power plant operators. They're very good at handling high stress, dealing with life-threatening situations, but in many cases they use a different language than the power engineers. In the process of working with power system operators for about 13 years with the simulator, I learned a whole set of terms like get under the voltage, weak bus, strong bus, open the weekend first, things I never learned, even though I had a PhD in power engineering. So the nice thing about the simulator is that whether you're an engineer, we can take the engineers and the operators and have them work together, and they can both learn from each other. The operators need to build a deeper understanding of the dynamics, why the system responds under dynamic conditions. The engineers need to build a deeper understanding of how an operator makes a decision in real time. We are starting to see some of the regional transmission operators for the first time are starting to hire power engineers to actually make real-time decisions. But in the past, in our country, a real-time engineer has been like an oxymoron, okay? But if you have military training and you've come up through a degree, military training clearly, if you're a junior officer in the military, you may have an engineering degree, you are trained to make real-time decisions. It's not like we as engineers can't learn how to make real-time decisions. We just need to have a chance to do it, especially with simulation. We have the power engineer and software engineer gap. Software engineers generally came up from computer science programs. They're familiar with Linux, with operating systems. They like to use languages like grep and awk and lots of different buzzwords because they really know how to make computer software work. And in general, at least in the last couple of decades, power engineers have been trained with nice high-level tools like MATLAB, but they haven't been working with languages in many cases which really require them to build a deep understanding of computer networking and computer operating systems and databases. So we've sort of seen a drifting apart of the power engineering programs from the software engineering programs. And one of the reasons people give is there's just so much to learn in this field and there's so much to learn in the power engineering field that really we need to give our engineers high-level tools like MATLAB. But unfortunately, that does create another gap. And then, of course, we have the software engineer and the power system operator gap. So one of the goals that we have here is to show the commonality of and start using a more common language between these different disciplines. Many of these programs are written in Fortran, which was a very popular language in the 70s and 80s, and some of them are very large, maybe 500,000 lines of code. And right now it's very hard to find a computer science graduate that has been using languages like Java, C++, C# to get excited about a large Fortran program. And so that's a major problem at this point. Another problem is it's difficult to share the models. When the models are created, it can take dozens of man-years of effort to build those models and displays, and they have been locked into the proprietary format of a single vendor. And so we tend to see that these companies model their own system very well, but they don't have any sense of what's happening in their neighbors. And as we saw in the recent Southwest outage in the Arizona, California area, things that happen in Arizona can actually propagate to affect what happens in California. And also in the Northeast outage in 2003, you can be running your system fine, but an operator 3-4 states away can make an error and your whole set of customers gets blacked out. We need to have a common set of models so that through training and studies they can anticipate those things ahead of time. So not only are the models difficult to share, the actual diagrams that visualize the system have been locked into proprietary systems. And clearly there's a move now to make sure that the same schematic diagrams, one thing that comes out of these blackouts is what NERC calls a wide area view, how to have a common view of the overall power system that all these different players can look at. The funding has been limited. As the price of systems has come down from $10 to $15 million to $2 to $3 to $4 million, the vendors don't have the opportunity to do the R&D that's been needed. There's a report from EPRI that's somewhat embarrassing. They say the total R&D in the transmission and development area is less than the R&D in the pet food industry. Oh, it should be quoted, but but the issue is utilities have to run things with very tight budgets and regulated rates, and so compared to say the air traffic control systems, which said let's just go out and build one system and contract Harris to build an entire traffic control system from one vendor and have it all standardized and sponsored by the government. We have a situation where we have 240 utilities with tight budgets, regulators very concerned about their rates, and they are trying to build 240 different systems from different vendors. So it's a whole different dynamic. I still believe that the private enterprise system is the best solution, but getting the right degree of R&D versus competition is a real unique challenge to our industry. You've got to have some level of investment in infrastructure, and that's why the DOE funding of the smart grid projects has been very useful. At the same time, we have to have a combination of competitive vendors and suppliers. And that basically is the unique thing about electricity as a commodity. Because electricity has certain characteristics which make it where it's just not widely, you cannot store electricity. There are limits on how you can transport it. It requires a lot of infrastructure investment. So it is still the last challenge to truly make it a deregulated, competitive industry and at the same time keep enough sharing of standards and technology and learning practices, which if it was purely private enterprise, those organizations would not be sharing anything at all. But in our case, it's one interconnected grid. So there's a certain amount of sharing that has to take place. And that's the challenge we continually have to face today. We've made a lot of progress, as you'll see, with introducing competition, but there's still major challenges that we have to face in the future. And then right now, as I mentioned, we have 5 suppliers with pretty much standardized products, and There's obviously the goal to continue to sell those products, and there's not a clear market signal right now about what's needed for the next generation. And again, building models of large regions continues to be a challenge. These systems can be difficult to use. Some of these applications you may need large regional operators may have staffs of 10 or 20 engineers keeping these applications running. A small utility often cannot afford a single engineer. Their manager of operations may serve part-time as the trainer. And so we have a wide range of sizes and budgets, as you'll see. We have not been through extensive testing. Right now it is still not possible to simulate the Northeast blackout in real time, which affected 50 million people. We need to be able to simulate a large blackout like that in real time, not just to train the operators, but to also validate the performance of these complex monitoring systems. The military uses extensive simulation to test all of its new equipment. They go through extensive human performance testing under very realistic conditions. And so, but they have much larger budgets. The entire budget for training marine pilots with simulators is $1 billion a year. Now that's not just the equipment, that's the staff to do that. That is way beyond what we're able to spend in our business. These systems are what I call fair weather systems. When the weather is good and all the data is coming on in and things are normal, they work really well. When the weather is bad and substations are taken out of service due to storms or floods and the data coming in is, of course, when we have storms, not only do the power system devices go out of service, the communications breaks. So at that point, we have a very difficult situation. When you need these systems the most, that's when sometimes the data is not available. And so having the systems that are more robust, that you'll hear the term self-healing grid, self-healing communication systems, that is when these tools are critical. And now there's also a catch-22 to market entry. When I was involved with ESCA, we would respond to opportunities or requests for proposals, and the request for proposal will say you have to have 3 or 4 systems running in the field for 2 years before you can be qualified to bid on our system. And so because these, so that's the catch-22. How do you become a new vendor when you have the catch-22 clause? And we saw OSI did that by upgrading systems, and but the systems of the future should be much more open. Someone with a really good application should be able to come along and plug it into a system and be able to show they can play as part of that game. And you see that with the Apple application market, the Droid market. They have platforms, and someone who has an application or a game can say, I can plug it into that environment. We don't have that platform yet available for third parties to plug their applications. DOE is starting that. They have a thing called Green Button where they're saying all this metering data available from these customers is available in an open format where people can write little applications. But that's just at the very lowest level of the data that's available from the meters. That whole concept, and they had a competition. Who could write the most innovative application on top of that metering data? The whole idea is to take that to much more advanced, where any of the data, any of the models is available, and we could have a green button for the system. But we're not there yet. Okay. The other area is that Metcalfe's law has not yet been applied. Moore's law is that the computer power technology will double every 18 months, and so we've seen tremendous increases in computer technology. Metcalfe's law, Metcalfe was a major player in inventing the Ethernet. His law is that the value of the network goes up as the square of the number of users. And you see that with Facebook. As you get more and more users, the value of that network goes up. Because these systems have been so expensive and they haven't shared data, we haven't seen that take off. In fact, these systems are so customized that there was a time where it seemed that if this utility bought from vendor A, the neighboring utility would my needs are different, and I'll tend to buy from vendor B. So we haven't seen the commonality of that happening. With the planning programs, clearly that has been, you would see with the first time a customer got a planning program from one of the planning vendors, because they were modeling the entire network, it only made sense that the other vendors would tend to purchase similar programs. So for example, you see the General Electric PSLF program is very widely used throughout the Western interconnection. The Siemens PSSE program is very widely used throughout the Eastern interconnection. And we'll get into those programs a little bit later. All right, so what I'll do now is we'll discuss an EPRI initiative called Grid Operating System 3.0. You have available to download some of those EPRI documents from the website, and we'll go through some of the highlights and some of the figures, which are all used, which were copyright of EPRI, and but are very, very useful to show the major changes that are going to occur. So in today's power system, basically we have central generation, whether it's hydro, nuclear, fossil, combined cycle, steam units, coal units, and they step up to a high voltage transmission system which delivers the power over that system to the residential as well as commercial and campus and industrial customers. And there's basically a one-way flow of electricity along the distribution feeders to those customers. Tomorrow's power system will be significantly more complicated. We will have intermittent large amounts of renewable energy, solar, wind. The California state standard is to have 33% of renewable penetration by 2020. One of the most ambitious state goals in the country. It is the most ambitious state goal in the country. But many states are also having what they call RPS, Renewable Portfolio Standard Goals. So we have these intermittent sources, which vary during the time of day, also being connected, along with the traditional centralized fossil and nuclear generation and hydro. That has been transmitted to customers now that may have local plug-in vehicles, either hybrids or pure electric, and those vehicles can both be a storage device. They can both receive power from the grid, preferably at night when there's more power available, or they could also, those batteries could be an alternate source of supply. So we have two-way flow at the distribution level. We can have solar panels on rooftops. So we're seeing companies that are going to customers and saying, we will install solar panels, we'll take care of the capital cost, and you will sign a contract with us, and we will guarantee you to have power at a lower rate than you would be getting from your grid supplier. In some cases, those systems can actually be feeding power back into the grid. We can have local wind generation. We can have local battery storage. Typically, the price is obviously high during the day when the demand is greatest, and it is less at night. There are actually parts of the country where they will pay customers to take the power. Why is that? There are times when it's hard to back the nuclear. During the nighttime, the load drops off so much, and we don't want to back down the nuclear units, and we have all this wind generation, and people are looking for an outlet to take that power it actually pays them it's economically beneficial for them to pay someone to take their power rather than back the units down or even take them offline. We can have smart appliances. One of the proposals is to actually, yes, in more and more areas where the states where the power is being deregulated, the idea is we send a real-time price to the customer. The customer then makes a real-time decision based upon that price about what devices in their home they should run. So we're seeing very smart appliances, washing machines, refrigerators, heaters that can actually be triggered on that real-time price. These systems may become networked. Distribution systems are simplified because they run radially. In the future, we'll see networks because that can improve the reliability. We'll see extensive communications. We can see basically communications right now typically is handled with very good monitoring of the high voltage transmission systems. In the future, we could be monitoring down to the feeder breaker, all the way to the customer transformer, and then even to the individual devices in the customer homes. So we will see an explosion in the number of devices that are monitored and where data is available by 2-3 orders of magnitude. So things become a lot more variable. The amount of data that goes up by 3 orders of magnitude, and we have many more players all engaged in responding to the signals of what's happening on the grid. There's also an initiative to extend the high voltage national grid. The green lines are 765 kV networks, which is the highest voltage used in the United States. We have 765 kV networks used extensively in the eastern interconnection. They're not used in the west, but as we look at where the wind is located, clearly it's in the heart of the country and along the coasts. So to get that wind generation all the way to the customers, there's been a proposal to build an entire 765 kV network. This is still obviously very much in the conceptual stage, but for example in Texas, we are seeing what they call CREZ, competitive resource renewable electric zones. And the idea is that through private enterprise, they encourage private enterprise to build transmission lines to take the wind in the northwest part of the state and move it to the population centers, primarily in Dallas and Houston. So we're seeing, again, in the past, transmission was always built by the regulated entities, but we're seeing innovative projects where private entrepreneurs are building transmission capacity and then selling that sometimes under long-term contracts, but more and more even under short-term hourly pricing contracts, to the fact that if they can bring low-cost power from this region to where it's needed, they can then charge for moving that power, just like a trucking company would charge for moving freight along a freeway. So what APRI has proposed is what they call Grid Operating System 3.0, where it will take care of the market operations, and we'll talk about markets, how central markets are very key to managing a lot of the electricity, along with the actual system operations of the transmission and generation, and that will tap into the smart transmission and distribution grid, which will also bring in the distributed resources. What we're seeing is aggregators are getting together and saying, I'll get all these distributed generators or storage and I'll create a virtual power plant or a virtual storage device because I'll take care of dealing with all those customers. There was one supplier was saying, I'll take all the forklifts which have batteries and I'll go around and negotiate with them to put in a device where those forklifts can either draw power from, give power back to the grid, and I'll go to the RTO and I'll say, look, I have a megawatt of controllable devices. I'll put the contract in place to let you control those devices, and then I'll obviously share some of the benefits with all of the end users. So we'll see aggregators come onto the market. And then, of course, we need to take care of the traditional centralized resources of the nuclear, the coal, the gas turbines, along with the solar and the wind. And that system will be used to manage tomorrow's bulk power system, which has a combination of centralized wind, solar, large compressed air energy storage systems are being proposed. One of the things that becomes more of a requirement is as we have intermittent devices like wind and solar, sometimes they're producing the energy at night when it's not available. So having more storage to take care of, to be able to accumulate that energy. We can't accumulate electricity directly unless it's batteries. How do we store that energy and make sure it's available at the right time? So we're seeing very innovative storage devices take place. There's one company that goes around and they basically convert industrial buildings. They take the air conditioning units on the roofs of buildings, and during the nighttime they freeze large amounts of ice with low-cost electricity. In the daytime they blow air across that ice and you get cooling during the daytime. So the idea that we can store thermal energy is also becoming more attractive. We will have building local energy networks. A building may have renewables, wind, solar, thermal storage, heat pumps, as well as plug-in hybrids and distributed. We have small called microturbines, a turbine that is capable of serving the energy for an office building of, say, 300-400 people, along with distributed storage. And that will have a master controller where, based upon the real-time price that's coming in, they will manage, not only the real-time price, but the forecast, they will manage all those devices to both reduce their consumption at high prices and even feedback when the price is higher. A number of universities are being very innovative. Universities have an ideal test bed. You have dormitories with large amounts of students. You can do things with those students to encourage them to run experiments that you can't do with your normal population. Right? So they're an ideal test bed. You have electrical engineering departments, mechanical engineering departments with lots of good talent, and then you have local resources like combined heat and power generators, utility storage, and so there are a number of campuses that are really stepping up and making their entire campuses available for smart grid experimentation. And then this can move up to a community level. The idea is what we call a self-healing grid where, and especially in today's age, as we see customers being subject to major storms and the power's not coming on for 2 to 3 days, even weeks, it's just a matter of time before an entrepreneur gets together with an entire community that may be in a remote area and says, look, let's connect to the grid, but let's also have our own local wind, thermal generation so that if the grid is not there, we are able to keep our flow of energy going with our own local microgrid and utility company. As the price of the solar and the storage and the wind keeps coming on down, this is becoming more and more realistic. So in tomorrow's distribution systems, we'll have these devices all integrated. There'll be a master controller, and there'll be the dotted lines are basically the flow of communications, and then this is the underlying electrical system. So the distribution systems themselves will become a lot more intelligent. Right now, we're all used to the fact that when the power goes out, we have to wait, of course, for the line crews to come on around. More and more utilities are putting in outage management systems that actually report when customers are out, and you get automatic reporting on the expected time for restoration of service. But as these devices are more economically available at that level, you'll need to have controllers and smart grid technicians and engineers that can run that community system. And so basically a lot of the computer technology, the communications, keeps on coming down in price, and what we need is the right training and the procedures to make this all work together. So what is being proposed is an architecture with multiple level controllers. A community local energy network, a campus local energy network, building local energy networks that are doing all the management of the local devices, and that interfaces up to the distribution system, which then interfaces up to the bulk power system. And so we'll talk about some of the numbers, but basically, instead of hundreds of thousands of points, we're probably talking at tens of millions of points being monitored. And the internet does that. The internet is able, think about Google Earth. And Google Earth is able to give you directions from any street corner in any city or town to any other point. So there's a tremendously complex network behind that. And then people are layering tremendous numbers of applications on that. So computers have the ability to do the modeling capability. What they haven't yet got the ability to do is handle all the real-time data flows and take care of the security. It's the volume of real-time data, the storage of the historical data, and the security is why we can't have something like Google Earth running a grid management system. But it's an inspiration. So in tomorrow's grid management systems, they've got to maintain this level of security, quality, reliability, availability of power, improve economic productivity, improve the quality of life. Really, if you think about it, customers don't buy electrons or kilowatts. Customers buy comfort, security, productivity, safety. It's ironic that a villager in a sub-Saharan African country will pay 5 cents to have their, they will pay 25 to 40 cents to have their cell phone charged with 5 watts of electricity. That's about 1,000 times. So we have these people making $1 to $2 a day, paying 1,000 times for electricity that we pay in the West. And they're happy to do that. I mean, if we raise rates in the West by 10%, customers get really upset. And that's because electricity in the West is a pure commodity. In these countries, it's a change in life. You can keep in touch with your relatives. You can figure out the right price to sell your crops. So my belief is that utilities have to look beyond the meter, look at how can they help improve safety, productivity, security of their end-use customers. And that's what we're seeing. Some of the leaders right now in this whole smart grid effort are getting together with groups of their communities and saying, okay, how can we work with you? And they're getting a lot of support. They just cannot roll out more technology and expect the customers to respond. So the innovative utilities are really looking at customers as partners and really figuring out how to work together. We're seeing that in the Northeast. We're seeing that in San Diego. And so that's the homeowner, the factory owner is the ultimate customer. How do we figure out how to work with them to make their life better? Things like I have an uncle in New Zealand. He runs a kiwi farm. Why not offer every day he has to figure out, does he go manually turn on all the sprinklers? Why not offer him a deal where we'll guarantee him a certain level of moisture content? If we can predict that, and do that on Washington State, if we can predict that it's going to rain next week, why spend a lot of energy and water doing the irrigation? So we've got to keep thinking beyond, and so it's a challenging time in utilities. Utilities are unique in that they have to work in a regulated market and deal with commissioners and regulators and justify their return on investment. They have been branching out into competitive markets. They have organizations that build power plants and sell energy competitively. And unlike any other industry, they have to deal with critical emergencies like in the military. They have to be there to respond. There's no business leader that has to react like a utility leader does when there's a hurricane or a storm that comes through and thousands of their customers are out of service and their transmission lines are down. And then they have to go to their neighbors who may somewhat be competitive and say, let me borrow your crews to come on in and put this system back together. So there are challenges in the utility industry for executive management that really are not paralleled in other corporations because of those three things. And we have a level of change that is unprecedented. Utility managers, executives will say this, but I think we're at a time when it really is true. The next 10 years could see the same amount of change as we've had from the time Edison built the first generating station. Okay, so I think we really are at a point where this change is going to be on us, and it's going to require the very best talented people with the best training. So I've talked about CIM, a common information model. I talked about Google Earth as an example. Why not be able to use that where you can zoom out and have a model of all the United States, all the 4 interconnections together, and have a high-level representation, and then be able to zoom down and include the feeder breakers, then go down another level to the customer transformer, and then another level to the actual appliances in the home. And one single model that is all put together. This is a vision. The technology is there, but there are many protocols, procedures, barriers to pulling this together. But that is what is needed to really make all these systems interoperate together. There is only one power system in the United States, so there really should just be one model that is openly available for all the different parties to use. And just as you can bring in different layers on Google Earth, we could bring in different layers of models to support different applications. So each of these applications, which we'll get into later, has different types of data that actually would be used on that model. A balanced power flow has probably the minimal amount of data, but when I say balanced, I mean that the 3 conductors all have an equal amount of current flowing. As we get into distribution systems, you may have a single phase, and so what happens as we go down to distribution levels, the current flow in each of those 3 conductors can be different. These models would have to be created for past, present, and future conditions. We need to be able to recreate and learn from the past. We need to run the present system, and then of course we'd like to study what can happen in the future. And here's one of the challenges is we can't make that model available to everybody all the time because of security reasons. And so we have to deal with that whole issue of how to give people the right level of access. So if we look at what it would take to handle that, for example, dealing with distributed variable generation will require us going down to what we call the feeder breaker level. It's that breaker typically at like 13.2 kV, 11 kV, that is actually running the distribution lines along the roads. And by modeling at that circuit breaker level, we can aggregate all the variable generation and say to the utility, that's the virtual power plant right at that point. If we don't model down to that level, we don't really know where that generation or load is located. So if we do some quick calculations, roughly in the US, there's 1,000 gigawatts of load. A gigawatt is 1,000 megawatts. A gigawatt is also 1 billion watts. So 1,000 times 1 billion watts is the same as 1 million times 1 million watts. So this terminology is really important in our business. So let's just take a little time and go through that. At the very lowest level, well, a typical customer, if they're driving, may have 2 kilowatts. All right. A light bulb is typically 60 watts. An air conditioner may be closer to 1,000 watts, which is a kilowatt. So just getting used to these acronyms is really good to understand in our business. So when we deal with customer equipment, we're typically talking with kilowatts. A utility is serving millions, so the utility deal with megawatts. They will talk about their peak load in megawatts, their total generation capacity in megawatts. So we think this, a megawatt is 1,000,000 watts. If a utility has 1,000 customers and each was using a kilowatt, how much is that? It will be 1,000 times 1,000, which would be a megawatt. So a good rule of thumb is that it's a megawatt for every person in their service territory. All right? So if a customer has 100 people, 1,000,000 people in its service territory, then 1,000 megawatts, because each of those 1,000,000 people is a kilowatt, then 1,000 megawatts is needed to serve that. Now, at this level, we're coming up to the entire United States. And so if we say that, and this we get by adding up the supply in the different regions, is that it is 1,000 gigawatts. And if we divide 1,000 gigawatts by 300 million people, we get like 3.3 kilowatts per person in the US. That is a very high amount of energy. So to do a top-level analysis, we take the kilowatts of load, and we say on average a feeder requires about 2 megawatts. So based on this, we could say if it's 2 megawatts per feeder and 3 kilowatts per customer, how many customers on a feeder? I'll let you all figure that out. Well, let's do it. It's 2 million kilowatts, 2 megawatts per feeder. So 2 megawatts per feeder is 2,000 kilowatts. 3 kilowatts per customer, we divide that by 3, we get 666 people per feeder. And Jay, you've worked with distribution systems. Is this math in the ballpark?
Pretty close. Good thumb rules.
Thank you. So sometimes we have to use thumb rules, okay, to kind of make a projection of what's happening in the future. So if we say there's typically 2 megawatts per feeder, 1,000 gigawatts, then we end up with 500,000 feeder breakers. And so why I'm doing this is that that's giving us an idea of the size of the model if we take the entire U.S. and North American power system networks, including Canada, and model it down to the feeder breaker. And that's not a very large model from a computational point of view, right? So like I said, it's mainly the political and the economic and the procedural things we need to go through to build that model. And we don't have someone like a Google that has said strategically, because we don't have millions of customers, it's not yet economic for someone to say, I will build that model and try and somehow make a rate of return on it. And because it's 500,000 feeder breakers, we are today already running power flows of the overall transmission network, which are 50,000 bus power flows. So I'm saying to go to the distribution feeder level, it's about 10 times the size of what we're doing today. But then to go all the way down to the customer transformer and to the devices in the home, that's probably another 1,000 or 10,000 times. So this is a very good interim step. Let's work together to model down to the feeder breaker with an interconnection model. So we have this vast model which is readily available to all the different applications. And then clearly we have the markets, the service providers, customers, distribution, transmission, having access to that to run their own applications. All right, so that is where I'll leave the vision of what's required for the future smart grid. Clearly, things are just at a very conceptual level. There is an enormous amount of work to be done, and I encourage you to join this industry and participate in these challenges.